Hello students, in this video we are going to discuss about some important topics in third lesson, magnetism and magnetic effects of electric current. First one is about solenoid. A solenoid is a long coil of wire closely wound in a form of helix. When current flows through the solenoid, magnetic field is produced. It is due to the superposition of magnetic fields of each turns of the solenoid. Inside the solenoid, the magnetic field is nearly uniform and parallel to the axis. But outside the solenoid, the field is negligibly small. Depending on the direction of current, one end of the solenoid behaves like North Pole and the other end behaves like a South Pole. The direction of magnetic field of a solenoid is given by the right-hand palm rule, such that if the current carrying solenoid is held in right hand so that the fingers curl in the direction of current, then the extended thumb gives the direction of magnetic field. Hence, magnetic field of a solenoid looks like the magnetic field of the Bohr magnet. Uses of solenoid. The solenoid can be used as electromagnets, which produces strong magnetic field that can be turned on or off. The strength of the magnetic field can be increased by keeping iron bar inside the solenoid. They are very much useful in designing variety of electrical appliances. Next very important application of solenoid is MRI scanning. In the case of MRI scanning, a superconducting wire in the form of solenoid is very much useful. Let us see how it works. MRI is said to be the magnetic resonance imaging, which helps the physician to monitor the treatment for a variety of abnormal conditions happening within the head, chest, abdomen and pelvis. It is a non-invasive medical test. The patient is placed in a circular opening and large current is sent through the superconduction wire to produce a strong magnetic field. This magnetic field produces a radio frequency pulses which are fed to a computer which produce pictures of organs, which helps the physician to examine various parts of the body. Next one is magnetic field due to a long current carrying solenoid. Here we are going to examine how far a long current carrying solenoid can produce a magnetic field. For that, we need an equation. In order to derive the equation, let us move on to the derivation. Consider a solenoid of length capital L which has n number of turns. In order to determine the magnetic field at any point inside the solenoid, let us imagine an Amperian loop A, B, C, D. From the Ampere circuital law, we can write closed integral B vector dot dl vector is equal to mu naught I naught. This is equation number 1. The left hand side of equation 1 is equal to integral A to B B vector dot dl vector plus integral B to C B vector dot dl vector plus integral C to D B vector dot dl vector plus integral D to A B vector dot dl vector. In this equation, the first term can be written as integral A to B B vector dot dl vector is equal to integral A to B B dl cos theta, because it is dot product. Dot product must be replaced as in terms of cos theta. Here you have to check the angle between the magnetic field B vector and the length of the Amperian loop dl vector. So in this case, both the magnetic field B vector and the length of the Amperian loop dl vector are lying in the same direction, so that the angle theta will become 0 degree. We know that cos 0 is equal to what? 1. So that this equation will become B into integral A to B dl. We know that integral dl is equal to what? L. So that the equation becomes B into L. The second term in the right hand side will become 0, because here the B vector and the dl vector are acting perpendicular to each other, so that the angle theta will become 90 degree. Cos 90 will become 0, so that the second term will become 0, because integral b to c b vector dot dl vector is equal to integral b to c b dl cos 90. Cos 90 is equal to 0, so that this equation will become 0. And look at the third term. Third term, integral c to d b vector dot dl vector is also equal to 0, because the portion CD of the Amperian loop is lying outside the solenoid. Usually the magnetic field outside the solenoid is said to be 0, so that this term automatically will become 0. And see the last term, integral d to a b vector dot dl vector is also become 0, because dA portion is acting perpendicular to the direction of the magnetic field, so that the angle between b vector and dl vector will become 90 degree. So cos 90 will become 0. Automatically this term will vanish. After substituting all these values in equation 1, we will get the equation as closed integral b vector dot dl vector is equal to mu naught into I naught, which is equal to b into L. Here I naught is replaced as n into I. It is because the solenoid is made up of n number of turns, and I is the amount of current flowing through the solenoid. So that the equation becomes mu naught Ni is equal to B into L. From this equation we can write the relation for the magnetic field inside the solenoid as B is equal to mu naught into N into I divided by L. In this equation, N by L is replaced by small n. This small n represents the number of turns per unit length of the solenoid. Hence, the equation becomes B is equal to mu naught Ni by L is equal to mu naught Ni. We know that N and mu naught are said to be constants. For a fixed current I, the magnetic field B inside the solenoid is also said to be constant. Next one is about toroid. What is toroid? When a solenoid is bent in such a way its ends are joined together to form a closed ring shape as shown in figure is called toroid. Now we have to examine about the magnetic field at point P, which is inside the toroid, and at point Q outside the toroid, and at point S, which is lying within the toroid. Now look at the picture. From the picture it is understood that we can see the open space interior to the toroid. In that space let us consider a point P. In this point, what will be the magnetic field that we are going to calculate? Let us do that. In order to calculate magnetic field at point P, which is nothing but BP, let us consider an Amperian loop of radius R1. The Ampere circular law for this loop can be written as closed integral B vector dot dl vector is equal to mu naught into I naught. Since the loop is enclosed, then no current flows through it, so that I naught becomes 0. So that the equation becomes closed integral BP vector dot dl vector is equal to 0. Hence BP vector will become 0. So we can say that the magnetic field inside the toroid in the open space is said to be 0. Next we have to examine the magnetic field outside the toroid. In order to calculate the magnetic field at any point, let us imagine a point Q which is lying outside the toroid. We have to consider an Amperian loop of radius R3. We have to apply the Ampere circular law for this loop 3, which can be written as closed integral PQ vector dot dl vector is equal to mu naught into I naught. We know that the magnetic field outside the solenoid is 0. Likewise, the magnetic field at any point outside the toroid is also said to be 0. So that the above equation becomes closed integral BQ vector dot dl vector is equal to 0. Hence, BQ vector is equal to 0. Next, we have to examine the magnetic field at a point S which is lying within the toroid. In order to calculate the magnetic field Bs at point S, we have to consider an Amperian loop of radius R2. Let us imagine the length of the loop L2 is equal to 2 pi R2, because this toroid shape symbolizes the circle. So that the length of the circle is what? 2 pi r. So that the length of the loop is also said to be 2 pi r2. And the loop encloses the current, which is equal to I naught is equal to N into I, because the toroid has N number of turns. Then the Ampere circuitous law for this loop can be written as closed integral Bs vector dot dl vector is equal to mu naught into I naught. Bs into closed integral dl is equal to mu naught into N into I, where closed integral dl becomes 2 pi r2. This closed integral dl indicates the length of the loop, so that only this is replaced as 2 pi r2. Hence the equation becomes Bs into 2 pi r2 is equal to mu naught Ni. Hence Bs is equal to mu naught Ni divided by 2 pi r2. Let us imagine small n be the number of turns per unit length, so that the term n by 2 pi r2 in the above equation is replaced as small n. Hence the equation becomes Bs is equal to mu naught into N into I. So we can conclude that the magnetic field at any point inside the toroid in the open space as well as outside the toroid in the open space is said to be 0. At the same time, the magnetic field at any point within the toroid will have some value. Next one is about Lorentz force. When an electric charge Q moves in a magnetic field B vector, it will experience a force. That force is known as Lorentz magnetic force. The equation for Lorentz magnetic force can be written as Fm is equal to BQV sin theta. The vector form of this equation will be Fm vector is equal to Q into V vector cross B vector. Next, properties of Lorentz magnetic force. From the above equation, we can say that the force Fm vector is directly proportional to the magnetic field B vector. The force Fm vector is directly proportional to the velocity V vector. The force Fm vector is directly proportional to sine of the angle between the velocity and the magnetic field. The force Fm is directly proportional to the magnitude of the charge. The direction of Lorentz magnetic force is always perpendicular to the velocity V vector and the magnetic field B vector. The direction of Lorentz magnetic force Fm vector on negative charge is opposite to the direction of the Lorentz magnetic force Fm vector of positive charge. If the charge is along the magnetic field, then the Lorentz magnetic force Fm vector is said to be 0. How is it possible? We know the equation for Lorentz magnetic force Fm vector is equal to Q into V cross B, which is equal to BQV sin theta. When both the velocity V vector and the magnetic field B vector are lying in the same direction, in that case theta becomes 0. In that case sin 0 will become 0, so that Fm vector will become 0. From this only we are saying that the magnetic Lorentz force Fm is said to be 0 when the charge is moving along the magnetic field direction. Next one is the definition for Tesla. The strength of the magnetic field is 1 Tesla if a unit charge is moving in it with a unit velocity experiences a unit force, which can be expressed in the form of expression as 1 Tesla is equal to 1 Newton second per Coulomb meter, which is equal to 1 Newton per ampere meter, which is equal to 1 Newton ampere power minus 1 meter power minus 1. Next one is about the circular motion of a charged particle in a perpendicular uniform magnetic field. Let us imagine a charged particle is having a circular motion in a uniform magnetic field. Now we have to examine the time period of the charged particle to complete one circular motion, and at what frequency the particle is vibrating while having the circular motion, and what will be the angular frequency of the particle to complete a circular motion. Let us imagine a charged particle of charge small q having a mass small m enters perpendicular to the uniform magnetic field B vector with velocity v vector. This particle will experience a Lorentz magnetic force which acts perpendicular to both the field B vector and the velocity v vector, so that the equation for Lorentz magnetic force can be written as F vector is equal to Q into V vector cross B vector. The magnitude form of this equation can be written as F is equal to BQV sin theta, because the bracket term is cross product, so it can be replaced by sin theta. So it will become BQV sin theta. Since the Lorentz force is perpendicular to the field, here theta becomes 90 degree, sin 90 will become 1, so that the equation will become F is equal to BQV. Hence, the charged particle moves in a circular orbit and necessary centripetal force is provided by the Lorentz force. So, this Lorentz magnetic force can be equated to the centripetal force, which can be written as BQV is equal to mv squared by r. Here mv squared by r indicates the centripetal force of the charged particle and BQV represents the Lorentz magnetic force. From this equation, the radius of the circular path can be written as r is equal to mv by b into q, which is equal to p by bq. Here m into v is replaced by the letter p, which indicates momentum. We know momentum is nothing but the product of mass and velocity. Let us imagine t be the time period taken by the charged particle to complete one circular motion. So which can be written by the equation t is equal to 2 pi r by v, which is equal to 2 pi mv divided by vbq. Then t is equal to 2 pi m by bq. This equation is called as cyclotron time period. Let f be the frequency of the charged particle when it undergoes the circular motion. The equation for frequency can be written as f is equal to 1 by t, which is nothing but, as we know, frequency is defined as the reciprocal of time period. From that only this equation comes, f is equal to 1 by t, which is equal to bq by 2 pi m. We can write the angular frequency equation as omega is equal to 2 pi f, which is equal to bq by m. This equation is called as cyclotron frequency or gyro frequency. From the above equations, it is understood that the time period, the frequency and the angular frequency all are depending on the charge of the particle, but not the velocity of the particle and the radius of the circular path. Next, some special cases are given. If a charged particle moves in a uniform magnetic field such that its velocity is not perpendicular to the magnetic field, then its velocity is resolved into two components. One component is said to be parallel to the field and the other component is said to be perpendicular to the field. Here, the parallel component remains unchanged and the perpendicular components keep on changing due to the Lorentz magnetic force. Hence, the path of the particle is not circle, but it is a helical path around the field, which is shown in figure. Next, we are going to discuss about the motion of charged particle under a crossed electric and magnetic field, which is shown in figure. Let us consider an electric charge Q of mass small m enters into a region of uniform magnetic field B vector with velocity v vector. Due to Lorentz force, the charged particle moves in a helical path. By applying proper electric field E vector, the Lorentz force can be balanced by Coulomb force. Here, the Coulomb force acts along the direction of the electric field, whereas the Lorentz force is perpendicular to the direction of the magnetic field. Therefore, in order to balance these forces, both the electric and magnetic fields must be perpendicular to each other. Such an arrangement of perpendicular electric and magnetic fields are known as cross fields. The force of electric charge due to these fields can be written as F vector is equal to Q into E vector plus V vector cross B vector. For a positive charge, the electric force on the charge acts in downward direction, whereas the Lorentz force acts upward direction, which is shown in figure. When these two forces balances one another, the net force will become 0. So that F vector will become 0. Hence QE is equal to BQ V naught. Here V naught is equal to E by B. This means that for a given magnitude of electric field E vector and magnetic field B vector, the forces act only for the particle moving with a particular speed B naught. This speed is independent of mass and charge. Some special cases are given here. If V is greater than V naught, then the charged particle deflects in the direction of Lorentz force. If V is less than V naught, then the charged particle deflects in the direction of Coulomb force. If V is equal to V naught, then there will be no deflection, but the charged particle will move in the straight line. Thus, by the proper choice of electric and magnetic fields, the particle with particular speed can be selected. Such an arrangement of fields is called a velocity selector. This principle is used in Bainbridge mass spectrograph to separate the isotopes. Next one is about cyclotron. Cyclotron. It is a device used to accelerate a charged particle to gain high kinetic energy. It is also called as a high energy accelerator. It is invented by Lorentz and Livingston. The principle behind the cyclotron is when a charged particle moves normal to the magnetic field, it experiences magnetic Lorentz force. Next, construction. It consists of two semicircular metal containers called Ds. The Ds are enclosed in an evacuated chamber and it is kept in a region of uniform magnetic field acts normal to the plane of the Ds. The two Ds are kept separated with a gap and the source S of charged particle to be accelerated is placed at the center of the gap between the Ds. The Ds are connected to high frequency alternating potential difference. Next one is working of cyclotron. Let us imagine the positive ions are ejected from the source capital S and it is accelerated towards D1, which has negative potential at that instant. Since the magnetic field is normal to the plane of the Ds, the ion undergoes the circular path. After one semicircular path in D1, the ion reaches the gap between the Ds. At this time, the polarities of the Ds are reversed so that the ion is now accelerated towards D2 with a greater velocity. For this circular motion, the centripetal force of the charged particle is provided by the Lorentz force. Then we can write the equation as mv squared by r is equal to bqv. Here mv squared by r denotes the centripetal force of the charged particle and bqv denotes the Lorentz magnetic force. After cancelling this equation, we can get r is equal to m into v divided by bq. From this equation, we can relate r and v as r is directly proportional to v. Thus, we can say that when the radius of the circular path increases, simultaneously the velocity of the particle also increases. Hence, the particle undergoes the spiral path of increasing radius. When the ion reaches the edge of the D, it is taken out with the help of the deflector plate and it is allowed to hit the target. Here is a picture which represents a cyclotron. Thank you students. Leave your doubts in the comment box.